Okay, this is the fourth video in the probability functions section. This is about the normal distribution, which is a really important probability distribution on which there are it's absolutely certain to come up in the exam, I would say. So what are we talking about? This is a continuous distribution, and as I said before, the probability of a specific value on a continuous distribution is not really a concept that we can work with. It's infinitesimally small, therefore it doesn't really have any meaning. What we're interested in is a range of values. Now this particular curve here I've drawn, it's got values under here. This is the value of the random variable, and this is symmetric about the mean. The mean here is 0. Unlike the binomial, which we've seen as could be skewed to the left if the value of the p parameter is less than 0.5, and skewed to the right if more than 0.5. But this is always symmetrical about the mean. So we've got a standard deviation of 1. It's not that easy to see from the diagram, but you have to take my word for it. Okay, so what are we looking at here? Well, this is a typical thing we may be interested in. What's the probability that the random variable described by this probability function is less than or equal to 2? Given that we're using this as conditional probability kind of notation, just to remind us what the parameters are, basically. So basically what we're looking at is all the space under the curve to the left of the red line. There's no particular significance that this vertical line kind of comes up from this point. In actual fact, this tail goes on and asymptotes towards 0. So there, even down here at -10, -100, there is still some space. It's not quite reached the axis. So how do we do this? Well, it's all this stuff is worked out for us on tables or calculators, usually calculators now, but just worth having a look at this table, I think, for standard normal distribution. Standard normal being mean of 0 and standard deviation of 1. So we go down here. These are the values of the random variable. These ones across are basically if we've got kind of subdivisions. So this, for instance, would be the probability that the random variable falls lower than 0.43. Kind of adds on to there. But what we're interested in is the probability the random variable is, we can say less than or equal to, or less than. It's essentially the same thing. Less than 2, that would be 0.97725. That's what we've got there. Okay, so that's good. Now we can do that with a calculator. Let's just do that. So if we get a menu 7, normal, cumulative, the lower of, we're going as far down as we like on the left, so big negative would be good, and then 2, and then a sigma, standard deviation of 1, and a mean of 0. Pop that in there and we get this figure 0.97725 to 5 decimal places. Okay, so that's how that works. What the calculator doesn't do is it won't tell you the mean and standard deviation if you know the area and the x values. So if you go into this and say, well, we know that the area below 2 is 0.97725, it won't come back and tell you what the mean and standard deviation is. So this is where in most situations we can just use the calculator. But when we're doing that kind of problem, we do need to know about the standard normal and how we convert, which is what I'm going to come on to now. Here we go. So here's the curve again. That's got the same red line in. Now, when we're dealing with a random variable that has a mean of 0 and a standard deviation of 1, we tend to use the letter Z, a big Z for that, as a name, if you like, for that random variable. An X really for everything else. Now the curves have the same shape, so we can apply the numbers as we wish. And in actual fact, what we've got is we can do the correspondence. So if we put the mean in the middle there, that's 6, and then this is one standard deviation. Now our standard deviation that we're talking about with our X random variable is 2, so that would give us 2 either side there, wouldn't it? That's 8 and 4. So what does that mean? Well, we've got basically in going from X, I mean, these two are correspondence. We can actually form one from the other if we know what the mean and standard deviation of this one is. And essentially, Z is equal to the X random variable minus the mean divided by the standard deviation. So, well, we can see that straight away, can't we? So if in case of the random variable 6, which is right at the mean, 6 minus 6 divided by anything is going to be equal to 0. 8, an X value of 8, then we subtract the mean, 6, and divide by the standard deviation, that's 2, we get 1. So 8 corresponds to 1 in our sort of our transformed variable. And then we got the reverse transformation there. So let's just have a look at an example. The probability that the random variable is less than or equal to 10, well, that's here, isn't it? Is given that the mean and standard deviation are 6 and 2. So that would be the same as the probability that the Z random variable is less than or equal to 10 minus 6, 10 minus mean, divided by the standard deviation of 2. And that says equal to the probability that Z is less than 2. Well, that's what we've done already. It's that area down there, isn't it? It's 0.97725. So we can see that that probability and that probability are exactly the same thing. Okay. So let's have a look at this example. The heights of a group of athletes are modeled by a normal distribution with a mean of 180 and standard deviation 5.2. So we're not bothered about the standard normal here. I know the diagram's got this on. That's just because I've picked it up from somewhere else, but I've written on the Z values here that we're interested in for this for the heights. But we've also got the weights, which I haven't drawn on there. The weights of this group of athletes are modeled by a normal distribution with mean 85 kilograms and standard deviation 7.1. Find the probability that a randomly chosen athlete is taller than 188. So that's what this is. Probability that X is greater than 188, given these parameters. Stick this in our calculator. So taller than 188. So this would be our lower value, and our upper value on the calculator would be some big number, 4 9s perhaps. And that gives us that. And then the probability that the weight is less than 97 kilogram, I've used Y because that's basically a different random variable. Given these parameters, again, just stick them in. Our lower value this time would be minus some big number, and our upper value will be 97. And that's giving us this number here. So fairly straightforward. Assuming that for these athletes, weight and height, height and weight are independent, find the probability that a randomly chosen athlete is taller than 188, like that, and weighs more than 97 kilograms. Well, they're trying to trip us up here. So we've got the sort of the complement of that. So basically we want 0.062, which we've got up here, times 1 minus 0.954, And that gives us this probability here quite small. Comment on the assumption that height and weight are independent. Well, they're probably not, are they? You know, they can, you end up with really tall, light people. And anyway, it's unlikely, obviously. Right, okay, let's kind of move on to this one. A scientist found that the time taken m minutes to carry out an experiment can be modeled by a normal random variable with a mean of 155 and standard deviation 3.5 minutes. Find the probability that the time is greater than 160 minutes. Well, we've drawn it on here. And I've marked that. That just comes with a diagram that I've imported. So I've put a Z there because that sort of denotes that is the corresponding Z random variable. But this is the random variable that we are interested in. So we're interested in the probability that's greater than 160. Well, 160 is up here, so it's somewhere in this tail up here. So we can stick that into the calculator in the same way. We get that. The probability that it's between 150 and 157, well, here we would have a lower of 150 and an upper of 157 with the parameters above. It gives you that. Then this last one is the value, find the value of m to one decimal place such that the probability that m is less than m is 0.30. So what we're interested in really is we're interested in some space down here. I mean, it's 0.3, so it's going to be less than half, because half the area is below the mean, isn't it? So it's going to be something from about here downwards that way. Okay, so but how do we do that? Well, we have to get our calculator up, guys. Again, and what we're looking at is the inverse normal. So if we look at the inverse normal, and we're looking at an area of 0.3. Yeah. And well, we do know the mean and standard deviation here. So the standard deviation is what's told up now, 3.5. And the mean is 155. That gives us 153.164 as we've got on there. So that basically is around about there, and it's saying that that the probability that falls below this value here and under the curve, that's that way. If the value that we take is 153.16, all that stuff, that is 0.3 of the total area under the curve, and therefore 0.3 of the probability. So that's that one. So we've used the inverse normal one. Now this one is an interesting one. Let's have a look. The heights of a population of women are normally distributed with mean mu and standard deviation sigma. It is known that 30% of the women are taller than 172 and 5% are shorter than 154. Sketch a diagram to show the distribution of heights represented by this information. Right, okay, we got our distribution, we got our Z statistic here. We've written the X statistics in here, such that that's 154, and the area under in this tail here is 0.05. That's what it says, 5% shorter than that. And it also says that that 30% are taller than 172. So that's 30% in this tail over here, which essentially means that this side of that black line has got area of 0.7. So he goes on to say, show that mu equals 154 plus 1.6449 sigma. Okay, so we don't know the values of mu and sigma, but if we know that this tail has got 5%, then we know that the Z value, okay, is going to be minus 1.644644. Got that wrong there, should be 6449. How do we know that? Let's have a look. So if we're going to go into here, menu 7, and if we go into inverse normal, so with for an area of 0.05, with a standard deviation of 1 and a mean of 0, then we've got minus 1.6449. Now, if we apply our conversion to that to get between this and the X value, then by subtracting the mean and standard divided by the standard deviation, okay, this value here is going to be equal to this Z value here. So X minus mu divided by sigma equals Z. Okay, so if we just kind of we rearrange that, we're going to get mu equals 154 plus 1.6449 sigma. Right, we've also got the same thing applied to this value here, because we know that we can work out, we can calculate that that's the Z value that corresponds, because we know the area, we work back to the Z value, and that Z value is going to be equal to the X value minus the mean, don't know the value of yet, divided by the standard deviation, for which we don't know the value, giving us that, and that gives us another equation for mu. Well, simultaneous equations. Obtain a second equation and hence find the value of mu and the value of sigma. So we basically, if we solve these simultaneously, we won't go into that, obviously eliminating mu in the first place, finding sigma, and then we can substitute sigma into one of these equations, find mu, and this is what we find, is that sigma is 8.298 and mu is 167.649. And if we look at it, it kind of makes sense there, doesn't it? It looks about right. So 167, so that distance would be, to there be 5, and the standard deviation is 8.2. So it all seems to fit together. A woman is chosen at random from the population. Find the probability that she's taller than 160. Well, this is just asking us to apply the fact that we now know the mean and standard deviation. So we're going to put those into our calculator in the normal way, and basically calculate this. So there are some examples of how we use the normal distribution and calculate probabilities. I mean, that's fairly straightforward. The trickier problems, I think, are those where we don't know the mean or the standard deviation, and therefore we have to find out Z values from the from the probabilities, i.e. the areas that we're given, and form an equation. In this case, we don't know either the mean or the standard deviation. In other problems that we might know one but not the other, in which case we don't need simultaneous equations, we only need one equation. But kind of see both of those situations equally, I think, in exam questions. Okay, so hopefully that has been useful. We're going to come on, there'll be there's a few examples videos on how we use normal distribution, so they'll be worth watching and working through. We're going to be developing the use of the normal and the binomial distribution a bit further in the following videos. So hopefully that's been clear, and we'll see you next time.